In this chapter, we're going to see similar reactivity to what we saw in the previous chapter, except all of our carbonyl groups will have another group attached to them. So we're not going to have just H's or alkyl groups attached to the carbon or the carbonyl. We're going to start to see these heteroatoms attached. So heteroatoms being an atom that is not carbon or hydrogen. So for these derivatives, they're called carboxylic acids, or their derivatives. We have the actual carboxylic acids themselves, which have that carbonyl connected to an OH. And so that OH group is going to be, the oxygen is going to be our heteroatom here. We're going to see what this actually does in terms of the reactions that these compounds can undergo. So we have our carboxylic acids, we have our acid chlorides, which are a derivative of carboxylic acids, because instead of an OH, they have a chlorine attached to the carbonyl carbon, but it's still a heteroatom, so we're still going to be able to see some similar reactivity here. Esters, this is another example. We have an oxygen, but on the other side of the oxygen, we have an alkyl group. In this case, it's just a CH3. We could have any alkyl group on this other side, and that would be an ester. So that's when we have a carbonyl and then an OR group. And that's in contrast to carboxylic acids, where that is an H attached to that oxygen. For the other derivatives, if we have an oxygen also attached to the carbonyl carbon, but that oxygen is attached to another carbonyl, so it's kind of this pattern where we have a carbonyl with an oxygen and then another carbonyl, we are going to be dealing with anhydrides. And what happens is that this whole group can act the same way that an OH can, or a Cl, or this OR group for esters. So we're going to see that reacting very similarly. Amides, they have the nitrogen, so this can be NH2 like we have here. It can be NH and then an alkyl group, or it could be a nitrogen with two alkyl groups. So those are all examples of amides. And then we also have nitriles, which the way that it's written here doesn't seem to really fit in. So let's draw out what is actually that CN group. So that CN group has a carbon that's triply bound to a nitrogen. And how we classify carboxylic acids and their derivatives is for that carbon of the carbonyl in all of these cases, the carbon is going to be bound to basically have three bonds to a heteroatom. So in these ones, though they have two bonds to one heteroatom and then one bond to another one in all of these derivatives, and so total of three bonds to a heteroatom in all of these. That makes them a carboxylic acid derivative. If we're applying that same definition to this compound, we do also have three pi bonds to a heteroatom. They're just all to the same one. And so these nitriles can actually undergo similar reactivity as our carboxylic acid derivatives as well, because it is also a carboxylic acid derivative. So those are the types of molecules we're going to be dealing with in this chapter. They're going to, the main thing that's going to really differentiate them is what conditions the reaction is under. So we're going to devote a lot of time talking about the different conditions and how the mechanism goes. So acid bases, that kind of thing. All of these are similar to the electrophiles we saw in chapter 6 because we have this delta plus that is at that carbon of the carbonyl. What we're going to examine first is we're just like we talked about aldehydes and ketones in terms of which ones were more reactive. We saw that aldehydes were more reactive than ketones as electrophiles because the ketones had two alkyl groups that were donating through hyperconjugation, decreasing that delta plus. They also were crowding out that carbon a little bit, so the sterics were important there. What's going to be important for this chapter is because we have heteroatoms next to it, the discussion of hyperconjugation or sterics becomes a little bit less, and what becomes a little bit more important is how much this heteroatom is actually contributing through resonance to this carbon of the carbonyl. So let's draw out an example of what that resonance would look like. So all the derivatives we saw on the previous slide, we would be able to take that heteroatom and do a resonance because its lone pair is next to a pi bond, so we can draw resonance like that. to get that negative on the oxygen and then have that double bond to that X group. If it was originally neutral, usually this X group is going to become positive at that point. And then what that's doing when this is donating electron density in like that is it's actually chipping away at that delta plus because this carbon is actually getting electron density from this atom in the form of resonance, which is actually a stronger effect than just through hyperconjugation. And so this ability of that atom, those heteroatoms that are next to this carbonyl to actually donate in, that's going to affect their reactivity. We're also going to see that heteroatom end up actually affecting the types of products we get out of this. So in the previous chapter, we saw aldehydes and with aldehydes and ketones, we were doing addition reactions. So we were kind of adding a new group to the carbonyl. We're making two new sigma bonds from that pi bond, that carbon oxygen pi bond. Here, we're going to start out the same way. So we're going to have the nucleophiles come and attack, and we're going to do something similar. Depending on if we have an acid or base, we might have to protonate that carbonyl first. In this example, we're under basic conditions just because that tends to be the shorter mechanisms. So what that's going to make, just like in the previous chapter, we're going to have that tetrahedral intermediate form when the nucleophile adds. So this is our tetrahedral intermediate. And then what's going to be new with this one, so we had that nucleophilic attack just like before. Instead of protonating this tetrahedral intermediate and just having that be our product, what's going to happen because of that heteroatom is that this tetrahedral intermediate is actually going to collapse. So what happens in these derivatives is that we're typically going to get to a point where we have one carbon that has sigma bonds to three different heteroatoms. And when that's the case, that's a very unstable intermediate and it's going to collapse to break the bond to one of those heteroatoms. And the one that's going to lead to our new product is if we kick off that heteroatom that was originally attached to the carbon of the carbonyl. So let's go ahead and do that. Our oxygen in this case is negative, so the oxygen that was originally in the carbonyl, that one's going to come down, and then we're just going to kick out that X group. That's basically going to replace that X group with whatever the nucleophile is. So structurally, we're going to substitute out that X group for the nucleophile. And this is the collapse of the tetrahedral intermediate. This is that new step that we're introducing for these mechanisms. And then what we're going to be left with is that X group. And we call this X group a leaving group because it was kicked out of the molecule and it left and it basically took the electrons from its bond that it had to the carbon, it took them towards itself. And so it has to be able to stabilize those electrons. So that's why we didn't see this type of thing when we were dealing with aldehydes or ketones because hydrogens, they're too small to actually stabilize those electrons. Carbons as well, not very electronegative, relatively small, pretty bad at stabilizing electrons. So we don't typically see those groups leaving. But heteroatoms, so atoms that are not carbon or hydrogen, these ones can actually stabilize that negative charge. So that's what that leaving group has to be able to do, and that's why these heteroatoms can do that, is that usually these heteroatoms are going to be relatively electronegative. They're going to be relatively large, so something like the chlorine, for example. They would maybe be able to do resonance, so something like with those anhydrides we saw, we might be able to have some resonance when that leaves. And then we also could have a case where that atom has other electronegative atoms nearby. And so these factors all might look a little bit familiar. So electronegativity, atom size, resonance, inductive effects, we could basically call that. So those are all the same things that stabilize conjugate bases. They're similar things that stabilize the leaving group. So conjugate base stability can be also tied to what types of things will stabilize these leaving groups. And so that's why we're going to have this type of reactivity, because we are going to have that heteroatom that can stabilize that charge. And so that reaction is basically going to substitute out whatever that heteroatom was originally with whatever our nucleophile is. So this is called a nucleophilic acyl substitution, and that's because we're substituting out the X group that we had for the nucleophile, and that's the type of reaction we're going to be dealing with in this chapter.